In this video, we are taking a look at Gauss Jordan Elimination and Gaussian elimination strategies to solve systems of equations via matrix. So I have here a system of equations that we are going to solve, and we are going to represent these values, the coefficients, in a matrix, which is a rectangular array of numbers. Each number is known as a matrix entry, and we arrange it as horizontal rows and columns. So we can take the coefficient values from the left sides of the equations and represent those as a coefficient matrix. So we can say for the first equation, 6, 4, and 3, where these values correspond with the coefficients, x, y, and z, the leading values, the coefficients for those variables. And then for the second row, we'd have 3, 2, and 1 for the coefficients corresponding with the variables x, y, and z. And for the last row, we've got 1, 1, and 1. So this is the coefficient matrix. And then we construct a corresponding column vector associated with the solutions. So our column vector will be 8, 3, and 2. So we talk about dimension when we talk about matrices and column vectors. So our matrix is a 3 by 3 matrix because it has 3 rows and 3 columns. The first value in our dimensions when we describe a matrix always corresponds with the number of rows, and the second value corresponds with the number of columns. We would say that our column vector here is 3 by 1 because there are 3 rows and 1 column. We like to be efficient and combine the coefficient matrix and the column vector into one matrix known as the augmented matrix. So our augmented matrix here for this system of equations is going to be 6, 4, 3, 8, 3, 2, 1, 3, where this last column corresponds to the solutions for each equation. And our last row will be 1, 1, 1, 2. So this is a 3 by 4 matrix corresponding with the system of equations that we have here. It's a 3 by 4 matrix because there are 3 rows and 4 columns. So let's take a look at how we can use this matrix form for Gaussian elimination. The reason that we like matrices is they're a little bit more efficient. So let's start with our augmented matrix. That is, I'll recopy it, 6, 4, 3, 8. Sometimes folks put a little dashed line here between the coefficients and the solutions. I'm not the best at it, so I'll usually leave it out. Then 3, 2, 1, 3, and 1, 1, 1, 2. So you can see this is more efficient than writing out the equations like we did previously because we don't have to worry about putting in the x, y's, and z's, or sometimes called x1, x2, x3 with the subscripts. All right, we want to get this into our row echelon or reduced form. So we are going to simplify the equations. So the first simplification I want to do is get a 1 as my leading coefficient in row 1. So I'm going to say multiply 1/6 by row 1. I'm using R1 with the subscript 1 to represent row 1. And I'm going to make that my new row 1. So then my new corresponding matrix is 1, 2/3, 1/2, and 4/3. So I've just multiplied each of those values by 1/6. As long as we apply the same constant to every value, that is just fine for us to do in terms of matrix manipulation, just like with the system of equations. Then my next move, let's see, I'll leave the matrix as is. I apologize for my computer handwriting. Then the next move I want to make is to get 1 is the leading coefficient in row 2. So I'm going to do that by taking -2 times row 2. Actually, I'm going to do -3 times row 1. I'm going to take -3 times row 1 and then add that to row 2. And that'll give me my new row 2. So you can go through those calculations and see that our resulting values will work out to be same first row, 1, 2/3, 1/2, 4/3, and now row 2 is reduced down to 0, 0, -1/2, -1, and row 3 for now is unchanged, so I'm going to go ahead and manipulate that next. All right, and so you can see each move is resulting in a new, more efficient matrix. Okay, the next move I want to do is to take negative row 1 and add that to row 3 to get a new row 3. So let's head over to the next sheet to see that resulting value. So that is going to give me this matrix. And you can see these are the kind of calculations that are probably better outsourced to technology, because as I try to do these calculations with fractions in my head, I'm more likely to make a mistake. So we are going to see next how we can outsource these types of arithmetic calculations to a computer. All right, you can go back and check my arithmetic, but I think that we are in good shape. So you can see from the previous matrix, the change I've made is in row 3, and in row 3, now I am getting closer to row echelon form. So now what I would like to do is get leading coefficient 1 in the second row. So this value right here, I want to make that a 1. So I'm going to do that by taking -2 times row 2. And as long as I'm consistent, that'll give me a new row 2. So I just have to make sure I'm consistent in both places here. So my new matrix is 1, 2/3, 1/2, 4/3 still up here in the top row. And then my second row is now much better looking because I've got a 1 here. So that -1/2 times the -2 gave me the +1. And then -1 times -2 gives a +2 here. And then row 3, I'll leave, I'd like to make row 3 a little bit better too. So let's go ahead and at the same time multiply row 3 by 3 so that I get a 1 here. So my new row 3 is going to have a 1 as its coefficient. So I've got 0, 1, 3/2, and 2. All right, so you might say, well, it looks pretty good, but it looks a little funny with row 3 having 1 as the leading coefficient in the second column, and row 2 having 1 as the leading coefficient in the third column. So to get into what we call the row echelon form, we want to flip-flop those. So we're going to say flip-flop row 2 and row 3, so that we now have our matrix as 1, 2/3, 1/2, 4/3. Then we've got 0, 0, 1, and 2. Oh, I didn't make my flip-flop. We've got 0, 1, 3/2, 2. And then in our last row, we've got 0, 0, 1, and 2. Ooh. So you're thinking about this in terms of a solution. Well, this is just saying z equals 2 from that bottom row. And then if you want to translate the second row back to an equation, this is saying, okay, y plus 3/2 z equals 2, and since we know that z is 2, we can say, okay, y plus 3 equals 2, so y must be -1. And then we can go back and substitute in for those values, y is -1 and z is 2, in the first equation to solve for x. So we can do our final solution here using that first row back to an equation, x plus 2/3 y plus 1/2 z equals 4/3, and then plug in our values. And those were z equals 2 and y equals -1. So we're going to have x plus 2/3 times -1 plus 1/2 times 2 equals 4/3. And so then we get, let's see, x equals 4/3 minus, if we move the 4/3 over, 4/3 minus plus 2/3, right? Because it's going to switch sides as we go over, and then minus 1. So this should end up as a 1. 6/3 minus 1 is 2 minus 1, or 1 here. Okay, so this is in what's known as row echelon form. So a matrix is in row echelon form if every row that consists entirely of zeros is at the bottom. If we go back to our matrix down here, this matrix doesn't have any rows consisting entirely of zeros. For every row that does not consist entirely of zeros, the first non-zero entry is a 1. So we see that on the diagonal, each leading entry is a 1. And then you want the leading one to be in the highest row where it's furthest to the left. So you want this triangular form with the ones on the diagonal. So we can also manipulate our matrix into what's known as reduced row echelon form. And that occurs when every column that has a leading 1 also has zeros in the other entry. So we would need a 0 where the 2/3 is in this column, and we would need zeros where the 1/2 and 3/2 are in this column. So we are going to look at how can we change this matrix to be in reduced row echelon form. So here's our matrix. It was 1, 2/3, 1/2, and 4/3, 0, 1, 3/2, 2, 0, 0, 1, and 2. And so we want to eliminate the coefficients that are above these values other than those 1. Those values are known as the pivot values. And so we are going to have to apply elementary row operations until we get zeros here. So we want to go through and figure out what to do to get rid of the zeros up here. Typically we use a computer to do that.